Hello and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge and satisfy some curiosity. I'm Laura and I'm joined by Antonia to talk about some unusual examples of using nuclear technology as a power source and figure out just how useful these alternative power sources could be. Now, Antonia, you work in the energy industry as an analyst and you consult on things relating to sustainability. So I guess you'd be interested in this from a decarbonisation aspect.
Oh, yeah, definitely. We have to explore different technologies to find the solution because there isn't a one size fits all. There are certain challenges of going down all one particular technology because it doesn't solve every problem. So, yeah, I've got to find out what is out there.
I'm with you on that. I mean, there's a whole challenge around net zero targets and trying to meet them without new technology could be really difficult. If you want to get to net zero by 2050, that's not very far away.
Not anymore, no.
No. I've learned about several types of nuclear technology that I think you might find interesting. So the first one is about new designs of nuclear reactors. So I guess you know, working in the industry, that we get reliable, low carbon electricity from our existing reactor fleet in the UK. But new ones could provide better ways of doing this or could do more than that.
Okay, I'm intrigued. I've heard of some things, they're not operating commercially yet, but what have we got?
So the UK is looking at alternative applications such as generating high heat for various industrial processes. So if you look on the government website, you do a search for like UK advanced modular reactor programs. It's a word I can't say apparently, modular.
You just need to break it down into smaller pieces.
Exactly, mod. So if you look for that, you'll find out that they've selected high temperature gas reactors as the chosen technology for future nuclear power plants. These can produce heats of up to 950 degrees Celsius, which is way more than you'd need for generating electricity normally. So most electricity generating power stations, they need to boil water or some other fluid or a gas. Boiling water only requires 100 degrees C, right? And that's what some reactors do to power their turbine. 950, obviously way more, could be used for way more things.
Going up to 950 degrees C sounds really useful. Yeah, when we generate steam, we still go above 100 because we're pressurizing it, because that way you get more energy density and you can transport it in smaller pipework. So it's more efficient for materials as well and easier to maintain than like massive pipes that are as big as your head or something bigger.
Yeah, I can see that, yeah.
Something that I'm looking at for companies, and it's a challenge to find something on the market that generates heat above, say, 160 degrees C, but people need heat, like 500 degrees C for, say, an industrial oven in the food industry, or furnaces start at 300 degrees and go up to 1,000, 2,000 for smelting metals.
Yeah, so some of those temperature ranges you gave, obviously 950 degrees C will exceed some of those. So could you use the heat from a nuclear reactor in your food oven or in your furnace? But then you mentioned smelting metals of a few thousand degrees C. That'll help you get there, I suppose. But then I would imagine you'd want a secondary source of heat to bump that up a bit more. But you can see how that would save energy, though, can't you? If you've got high heat coming from a nuclear reaction, and it's not radioactive, by the way, the stuff that comes off it, because you've got some sort of cooling loop to just extract the heat and leave the radioactive stuff where it is.
It would be what we call an indirect heat exchange rather than direct heat exchanging, mixing reactive materials with the medium you want to transfer the heat into.
I'm glad you said that more succinctly than I was waffling around. Thank you.
When you spend all day talking about energy and mechanisms for it, then hopefully I know a bit of lingo to make it make sense to other people working in it. The thing is, even if you did have that technology, it just won't happen overnight because you've got to reconfigure things. So if you didn't have a direct swap and you needed to create some sort of hybrid system with like heating it up to 950 and then higher, then you've got to adapt your equipment.
Yeah, so I guess you could either use the electricity from the reactor, if you're using it to do both things, so you could use it to power your turbine when you need it, you could use it to direct the heat to do other things elsewhere when you don't need the turbine.
Yeah, there are some things doing that currently, which we combust fuels for. So we're kind of relying on a fossil fuel or biomass or biogas, which you combust. But if we're going down the sort of decarbonised electricity route, I wasn't sure how we get there.
To decarbonize, yeah, I guess it would need these less straightforward, more integrated ways of using energy. I mean, I can see that, like, let's say that you're powering your turbine to generate electricity from the nuclear reactor, and you can maybe store that power somehow. And then if you then divert the heat from the nuclear reactor, you can then use that electrical power to increase the heat even further using, well, I guess some sort of resistance heating. There are probably smarter ways of doing it, though.
Yeah, the most efficient way that we know of is taking advantage of thermodynamic properties in certain fluids, so refrigerants, what we call them refrigerants, but they're hydrocarbon or hydrofluorocarbon organic mixtures. We use them in something called a heat pump. It's a thermodynamic term where you put in work or electricity and you get more units of heat. So your efficiency is more than 100%.
Oh,
Wonderful.
yeah, I feel like that's saying it kind of produces extra energy from the ether like a perpetual motion machine.
It's to do with the pressure of the fluid. It's not magic. It's works in thermodynamics. Can't say I really understand it. It's kind of like if you think you understand quantum physics, maybe you don't.
Yeah, we went over some of this in our thermodynamics episode a while ago, and it took us a bit of interesting discussion to try and figure out how these things work back then. And I think I've forgotten a lot of that information. Need to revisit that episode.
Yeah, I know the basics of it works, so
Yeah,
it's something we can do.
some pretty smart physics. And yeah, I guess nuclear could be used for lots of other things, so not just supplying that heat. I guess we haven't really talked about other applications. You could use it to make fertilizers, for example. I think some of that would involve using the heat and the electricity from the nuclear plant to produce hydrogen by splitting water, and then you can use some of that to make fertilizers. I can see there could be applications for making plastics from CO2 as well. If you're capturing the CO2 from the atmosphere or from water, you combine the hydrogen with the CO2 in some novel way that may use high heat.
Another thought that came to mind is there's a lot of gas used in incineration, trying to get municipal solid waste into a form that is got safe emissions. You have to combust and heat everything to above 800 degrees.
I did not know that, and I've always considered that waste is just buried in the ground and it's turned into landfill and that's it. But I assume there's only so much capacity for doing that, and a lot of it doesn't break down that quickly. So I guess is that the advantage of burning it?
Yeah, and you get energy out of it again.
Are we going back to perpetual motion machines? I'm guessing it's less energy out than you put in.
Yes, that's correct. Yeah, if you're running out of space, you can stick it in an incinerator, but it's also for things that you don't really want to just landfill. If it's contaminated, you don't really want to just leave it in land because then it could leach into waterways or leak into soil. And so it's a inverted commas clean way to treat your waste.
I see. In the future, there's this idea that we could have something that they're called industrial clusters. It's basically where you have all different industries working on the same site that can use byproducts from that other industry. So you could have your nuclear reactor that's either supplying electrical power or supplying high heat. You could have that coupled to a hydrogen production plant, a carbon capture plant. If you've also got gas fired reactor on site, you could have your municipal incinerator there as well. You could have food industry with the ovens.
Yeah, it's something that could be really interesting. I think in the past that would have been more common as well because people would say gather around a water source to use water as a I can't think of the word, a water wheel.
Yeah.
And then you would get mills for flour, and then you have bakery, and you kind of have all these basic industries all clustered together. Jasmine was actually doing some research in industrial clusters, I believe, and decarbonisation plans.
Oh, okay. So what we're doing now is just almost like a weird blip in human history where we've distributed everything and it's proved to be not very helpful. So we're going to bring it all back together.
Well, people are still clustered, but I think there's a lot less local networks, I guess, because you could share resources, like you said, and now there is maybe more benefit to combining resources to make a pipeline rather than just kind of everyone all doing their own thing.
Okay, so a more advanced version of having a water wheel that supplies different things with the same sort of power.
Yeah, but I guess if we're looking at industrial clusters, so how big are these high temperature nuclear reactors?
Well, the thing is, there are so many different designs floating around the industry at the minute that they could be pretty much any size.
Hmm,
So you've obviously, you've got the really big ones that we currently have today that some of them, I'm sure they're like the size of a small town. This is my impression of the ones that I've driven past. You could have much smaller ones as well. So you've obviously got technology that's built on the reactors that are used to power nuclear submarines and some ships that have got nuclear reactors to power them. They're pretty small. So you could maybe even put them in the middle of towns or cities in the far future. They've a small footprint and they're going to be designed to be like uber safe. So you could be living next to a nuclear reactor perfectly happily, having that power your city and maybe your industrial cluster as well.
so are we gonna have one in our back gardens?
Who knows? Maybe if they're literally just a thing you can get off the shelf and take home, and an engineer can come out and service it. Same way that your car works now, pretty much. If you looked under the bonnet of your car, could you do anything to it at all?
No.
So yeah, you never know.
Yeah, so it sounds like the development of these high temperature nuclear reactors could mean the future looks very different. Little nuclear clusters, just like a nucleus.
That's one way of looking at it, with satellite communities being electrons that do different things. I don't know. I know where we're going with this analogy. I feel like we should move on.
No, it's just an image, isn't it?
Yeah, so I mentioned there are other different technologies out there beyond these reactors. A good one that I'm aware of from working at the National Nuclear Laboratory is space batteries.
Okay. Are they batteries that work in space?
They're probably not what you think of as a traditional battery, like lithium ion battery that's got cells in it and electrochemistry happens. Instead, these use the decay heat from an isotope that's radioactive, and that provides a small amount of power, but it's enough for space probes. And the way that works is because you have that heat, you've got the heat source, and you've got the cold of space. If you've got a thermoelectric module, I can't say that word either. The modular is really escaping my brain today. You've got a thermoelectric module or a thermoelectric device in that temperature gradient. You have a voltage difference, a voltage as a current. I'm also completely mashing how electricity works. Voltage and current are obviously two different things.
They are. So an isotope decays and it releases heat,
Yes.
and we get electricity out of that?
The cool science thing here isn't necessarily the natural radioactive decay, it's the thermoelectric module itself. These work a little bit like solar panels, where energy is imparted and then that causes the liberation of electrons that can then flow in a certain direction because of how the thermoelectric module is designed with semiconductor materials. So you have bits that are naturally positively charged and bits that are naturally negatively charged.
P and N type cells.
Yes, PN junctions, yeah, pretty much.
Okay, I kind of understood that.
Good, I'm glad. Apart from the bit where I'm like, yeah, voltage and current used interchangeably, obviously very wrong.
There was flow of charge.
Exactly, which is driven by the voltage, which is a potential difference. That's what I was trying to get at.
So this, I'm gonna guess, could be quite a lot smaller scale than the first example you gave.
Yes, so if we're talking about powering space missions that generally need small amps in a smallish voltage compared to nuclear reactors that supply a phenomenal amount of power.
Yeah, I follow.
Good, I'm glad. I have another small scale example.
Okay,
There's some emerging technology that's known as diamond batteries.
shiny.
Sounds very exciting.
It does.
So these take graphite that's been used as a moderator in the core of some existing big-scale nuclear reactors. The graphite has carbon in it that undergoes beta decay, which obviously produces electrons from that decay. And you could use electrons to power things, of course, electricity. When I was looking into this, it looks like it was something that was considered for powering pacemakers that would be inserted inside of you, and then they found, I think it was just more efficient ways of doing it or more useful ways of doing it, so they stopped looking at it.
Well, I like the idea because you're kind of completing that full life cycle of a nuclear fission plant. This is different though. The technology or the nuclear mechanism is different between the diamond and the space battery.
Yeah, so I think the space battery is typically undergoing alpha decay and giving off heat as it does so, and it's the heat that's used. The alpha particles have got a really low range, they don't penetrate anything, so it's the heat that's important. Whereas the diamond batteries are giving off electrons effectively, or a charge which is used to produce the current.
Okay. Is this the same as americium in smoke detectors?
Yeah, it pretty much works in the same way as the diamond battery. The americium gives off electrons that's detected by a detector on the other side of the smoke detector. I'm saying the word detector too many times. And then when smoke gets in the way, it affects the flow of the electrons, and your detector goes, hey, there's not enough electrons getting through, and starts alarming you. So, yeah, similar principle. It's the flow of the electrons from the radioactive source.
So right now, well, I say one of the ways we power stuff in space is with solar panels.
Yeah, and that seems to be a very common thing. You often see satellites with those big solar panel arrays on them. My understanding is these would be really good for deep space missions, which is way beyond where sunlight reaches, or places that just don't see sufficient sunlight, like I say the dark side of the moon, when the moon side is not in sun.
Then yeah, that would be quite a problem.
Yeah, basically similar to here on Earth at night when the sun's not shining, you need an alternate power source.
So if we're having deep space missions, I was trying to get an idea of what kind of power do these units use, and partly inspired by Apollo 13. So I found ALSEP, which was their experiment station hub thing that they leave on the moon. Everything took less than 75 watts of power. Or it said less power than a 75-watt light bulb, which to me just said less than 75 watts.
That is true, but I guess if you're not entirely sure what uses 75 watts, it's helpful to know it's, I guess, an old school light bulb, because LED ones are much lower power consumption, aren't they? So it's a pretty small amount of power, in my opinion. Even though I've just said LED bulbs use less power, it's still not a massive amount. And you mentioned the Apollo 13 movie. I think I watched that recently as well. They were talking about keeping the current below 20 amps when they were powering up the command module after the explosion, and they were getting ready for re-entry back to Earth. Now, we just said that current and voltage aren't the same thing.
No.
20 amps refers to the current, and you need to combine that with the voltage to find out the power use.
Yeah, the American National Air and Space Museum had some of the fuel cells that were used in Apollo. It seemed like they would give the command module, which is the thing needing 20 amps, a power of up to 2,300 watts. Still, not very much.
No, it sounds like it's about enough to power 2, 3 modern kitchen kettles, or maybe a few microwaves that you might have at home. Why you'd want that many kettles and microwaves in your home, I don't know, but hey. But yeah, compared to those massive nuclear reactors I was talking about, the like megawatts of power, small diamond batteries do small things.
What's the benefit compared to a conventional battery, though?
From what I understood, the command module on the Apollo mission used fuel cells that rely on combining hydrogen and oxygen to produce electricity and water, and they eventually will run out. You've only got so much hydrogen and oxygen on board, and the astronauts were consuming the water and then ejecting it into space. Maybe they could have developed a way of doing that so it was a closed system. I don't know. It was the 60s and 70s, and my brain is thinking of too many things. In comparison to those fuel cells that run out, or traditional like lithium-ion batteries that need to be recharged, diamond batteries, because the radioactive source is radioactive for a really, really long time, like thousands and thousands of years, the diamond battery will last for thousands and thousands of years. In comparison, how long does your smartphone last? What, like 4 days? Less than that before you have to recharge it? I suspect the power output from the diamond battery would be a lot lower than those fuel cells on the Apollo missions, though. So I guess it's about choosing the right power source for the right requirement.
Yeah, so I was looking them up for a bit more specification or statistics and numbers. At least the ones being developed by Bristol University, on their website, they said the diamond battery could last for thousands of years, providing really low power in comparison to a conventional AA battery, which would provide maybe 30, 40 times the power it would only last a day.
So that kind of matches with what I was thinking. To me, an AA battery would usually be considered low power if thinking about what you use it for at home.
Definitely.
But then the diamond batteries, and I guess the space battery that I mentioned that uses heat, they're probably even lower power, but then that's fine for some long space missions, I guess, because they've optimized the power requirements of the instrumentation.
I can think of some examples where it could be useful on Earth, though.
Okay, I'm intrigued.
In my investigations looking for energy saving measures, you could get smart thermostatic radiator valves, so it could turn the temperature up and down without you having to manually adjust it. But if you have them powered with AA batteries, they run out after a year or two, and you've got to change them. And if you've put them in a building with lots of radiators, say student halls, any big office building with lots of radiators, someone has to go and change all those every 1 or 2 years.
And I guess all that time would add up. I could imagine it's fine in your own house where you've maybe only got 7 or 8 radiators.
Yeah.
Yeah, someone would have to do the maths on how long would that take, and is it really worth it? Or do you just stick with something that's lower tech and doesn't require a battery? Or go for the space tech?
It could be space tech. There is a solution where it's harvesting the heat and supposedly could last 10 years. But the fact that someone had some bad experiences with AA batteries was enough to put them off this.
Yeah, I mean, I've been looking at getting some battery-powered lights for decoration around the house. It's Christmas time. Very related to traditional Christmas decoration. And you can get those like little tea lights, things that you put in little votive candles, and it looks pretty.
Oh, yeah.
And they can be battery-powered, and the light bobbles around a little bit, simulates
yes,
candle.
yes, where they look like they flicker, but it's just a battery.
Yeah. But then I was thinking about how long the battery would last and how long you'd have to replace them, and it didn't seem worth it. I figured it was easier to stick with traditional candles that you light with a match.
Okay, here's going to be maybe a dumb question. Is there any scope for nuclear or radioactive things that glow and could be your little light source instead?
I'm not sure there are radioactive things that do actually glow. It's normally that radioactive particles or energy from the radioactive source is interacting with another chemical that causes that to glow. The glow in the dark stuff that I have on my watch, that's not radioactive anymore, but it used to be way back in the day, didn't it? It was a radioactive isotope, the name of which escapes me, but it should be right in my brain. You can tell my brain's not working very well today.
Is it radon?
That's a gas. I don't know. I think we need to look into the chemistry a bit more, though.
Oh.
I feel like we're just starting to ramble about weird things. I do like the idea of a diamond-powered flickery candlelight, though. Seems totally unnecessary to have one that would be powered for thousands and thousands of years.
Would the light part of it die before the power part?
Maybe.
You'd have to replace the bulb.
I feel like some sort of whole system analysis of faults and failure rates would be coming on, which I feel is a totally different episode.
And might be a bit overkill for a little fairy light.
It's a thing I would find useful, but I feel like we should stop there, because my brain has started to melt about 20 minutes ago. It's seemingly not functioning today. So we've discussed some ways that future nuclear reactors built here on Earth could supply heat for lots of industrial applications, not just generating electricity from a turbine. And we've learned about some smaller scale applications that are being used to power space missions, and we would maybe want to see them used on Earth too. The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.